Welcome to today's lesson. We're going to be talking about different wave characteristics. One thing we want to mention first before we get into anything else is that when we show some waves, some of the demonstrations are going to be talking about wave fronts. We want to make sure you understand what those are. So here what you see are some waves from the side, and you can see the up and down patterns, the crests and the troughs. We're used to those. But when we talk about wave fronts, usually that's, well, what would happen if we viewed this from the top? So if we go ahead and switch to the top view, the exact same waves could be viewed like this, where in this case we might envision the bright parts as crests and the dark parts as troughs. So we'll be taking advantage of that. We want to make sure that you understand how those relate to the wave patterns we've been drawing before. As we talk about waves today, part of our discussion is going to be mentioning measuring angles as the waves approach boundaries or barriers. And something that we take advantage of is something called the normal line. Now, normal is a word that they use in math class, and it simply means 90 degrees or perpendicular. So if we have a barrier like this, to draw a normal line, it's very simple. I am having to eyeball it, but I think we can get it pretty close. The normal line would be 90 degrees perpendicular to that surface. Now, when we have situations where you have curved surfaces, the normal line is going to be changing the exact orientation that you see it as the surface curves, and the surface changes its direction as well. So for example, if I were to pick this point, a 90-degree angle at that specific spot would look like this. So then this would be our normal line for that specific point. But over here, 90 degrees to that is something in the neighborhood of this, so that's about 90 degrees there. And then right here, 90 degrees would look like this. So again, as we discuss normal lines, just want to make sure that you understand what we mean. 90-degree angles to the surface, and if you have curved surfaces, then that normal line will be at a slightly different angle depending on where you are along the surface. So now it's time to start our discussion of wave behavior. For the wave behaviors, so there are 5 that we're going to be discussing today. Actually, we're only going to be discussing 4 because we've already discussed a lot about interference. But you see reflection, refraction, diffraction, and absorption. So these are what we're particularly going to discuss today. Now, we don't need to spend a lot of time on reflection, the first wave behavior. You do know that as a wave hits a barrier, it reflects back. You will also recall that as a wave comes in, and it reflects off a solid barrier, it reflects negatively, so any crests become troughs and vice versa. Now that was in one dimension. If we have waves reflecting in 2 or 3 dimensions, well then they can approach at angles, and so we do need a short discussion about that, but basically it's pretty simple. The angle that it comes in at is going to be equal to the angle it reflects at, but it's going to be measured from the normal line. So we're going to take a moment just to talk about how to draw that and how to make sure that you're measuring the angles correctly using that normal line. So as we were just discussing reflection, here's an example if we were to ask you to draw these different situations in order to show what you understand. What we have here is a strong barrier, so this is not anything that the wave can pass through. This is something that the wave is actually going to bounce off of. It's going to reflect, and the angle that it comes in is called the incident angle. Now remember that that's the reason we draw the normal line. The normal line is always 90 degrees to where the wave hits. The barrier that the wave hits, and when you measure the angle, it's always measured between the normal line and the direction that the wave is traveling. So this is the arrow representing the velocity of the wave. So from here to here, the velocity to the normal line, we would call that the incident angle. And if you're not familiar, this is a Greek letter theta. It's very much like x in math class. They just tend to use theta instead of x when we talk about angles. Now, as we said, during reflection, it's very simple, that the angle it reflects at will be equal to the angle that it hits at, the angle that it was incident at. So if we were to draw that, I am going to have to estimate here, and I'll try to make it as good as I can. But what we were saying here, then if you measure the angle that the wave reflects at, we would call that the angle of reflection, that these two angles should be equal. Now if I were going to actually picture this as the waves that were coming up, you could draw the wave fronts as they approach the barrier, and then as they reflect, the wave fronts would look like this. Same spacing apart. The only difference is the direction that they are moving after the reflection. So what we should say down here is, just as a final reminder, that during reflection, the incident angle is going to be equal to the angle of reflection. The next wave behavior we want to discuss is refraction. Refraction is used quite a bit, particularly with light. When waves refract, they travel from one medium into another, and if the speed is different in the next medium, or if something simply about the medium changes, like stretching a string, well then, as the speed changes, some other effects can occur, particularly the bending of the wave. So in light, refraction is what's responsible for glasses and contacts being able to change the direction of light in order to allow you to see. I think everybody's seen this example where when you take a look at an object where part of it's in water, part of it's out of water, it appears to be coming from different places due to the bending of the light as it travels between media. And so here we've got a one-dimensional picture of a wave coming in, and you can see that this is the fast medium. The wave is moving pretty quickly, and then it approaches the slow medium. It slows the waves down, and you see some of the changes that occur. So let's go ahead and take a look at how you can draw those using the wave fronts and some specific information that you need to know. So as we discuss refraction, we're going to take a look at three similar but slightly different situations. In this first situation here, what we are doing is we're moving from a fast medium to a slow medium, and here we've got the boundary. Remember the difference between a boundary and a barrier. A barrier blocks the wave from passing through. A boundary allows the wave to pass through. But it is usually marking the difference between two different mediums, and as the mediums changes, that changes the speed. So in this case, we have the normal line, and if you take a close look, the wave velocity is actually heading parallel to the normal line. So it's hitting the boundary straight on. So if we're moving in a fast medium, we can go ahead and draw what would those wave fronts look like as they come in. Now as they slow down, as you saw in the animations before, those waves are going to get closer together. So as they pass through the new medium, you have smaller wavelengths. Remember that each line basically represents the crest or the trough of the wave as you watch from above. So we see two things changing here. First of all, we said this is a fast medium, so the incident velocity is pretty big. We'll represent that by a longer arrow. Slow medium, we'll draw a shorter arrow to represent a slower speed, a slower velocity. So we'll call that the refracted velocity. And then if we take a look at the wavelengths, here the wavelength is about that long. So you've got your incident wavelength as it was incident or coming into the boundary. And then as it slowed down, the wavelengths got closer together. And so here you have your refracted wavelength, which is noticeably shorter than the incident wavelength. If we were to summarize down here, when the wave comes in, parallel to the normal line, basically 90 degrees perpendicular to the boundary, then there are two things that you should notice if it goes from fast to slow, and that is that the incident velocity will be greater than the refracted velocity, and that the incident wavelength will also be greater than the refracted wavelength. Now here we have refraction in two dimensions, meaning that because it approaches at an angle other than straight along the parallel to the normal line, we are going to see some bending of the wave. So the three things that we can see changing here are direction, the angle of the wave, the speed of the wave, and the wavelength. In the previous video you saw that the only two things that changed were the speed and the wavelength. Now that we're approaching at an angle, the angle is going to be different. So let's take a look at some of the specifics as waves approach at an angle and refract. For our second refraction example, instead of the wave coming in at a 90-degree angle striking the barrier directly, it's coming in at an angle. And so again, when we are taking a look at this before, we'll just remind you before, there was no difference between the normal line and the incident velocity, so the angle between them would be 0 degrees. But in this case, now it is coming in at a definite angle, and remember we do measure the angle between the wave velocity and the normal line, so we can go ahead and label that. Here is your incident angle. Now if this boundary was actually between mediums where this wave was moving at the same speed, the wave would not really change at all. It would just continue. It's just moving from water into another section of the water, but the water is all the same. If that were to happen, then what you would see is no changes. The wave would just continue on in a straight line. However, that's not the situation here. In this situation, this is the boundary between where the wave can move fast and where the wave is moving slow. This is very similar to when light passes from air to glass. If you look at a prism, if you look at thick glass, you'll see that it looks weird. These images seem to be coming from the wrong space, and that's because the wave has changed direction. And so as you go from a fast medium to a slow medium, the easiest way to think about what's going to happen is if you take a look at the angle, since it's slowed down, everything else that we measure is also going to get smaller, including the angle. So instead of going straight, the angle is going to get smaller. And remember, since we're measuring the angle from the normal line, to get a smaller angle we have to get closer to the normal line. So it will look more like this, where this would be the refracted angle. And if we were to draw some wave fronts just to show what the waves would look like, if these were water waves going from a fast part of the ocean into a slower part of the ocean, what you would see is that here the waves are fairly spread apart, but as it slows down into the slower spot, the waves do get closer together as they bunch up. The waves in front are not moving as fast as the waves behind, so the waves behind have caught up to them, and so those wave fronts are noticeably closer together. So if we were to summarize the changes that we see, the first, well, actually, we should also say here the velocity, the incident velocity was fast, and here the refracted velocity was slow, and again we represent that with a slower arrow. So we can summarize here. If you go from a fast medium to a slow medium at an angle, as we saw in the last example, the incident velocity is going to be greater than the refracted velocity. The incident wavelength is going to be greater than the refracted wavelength. But what's new is when you come in at an angle that's not zero, what we also see is that the angle that it approaches, as measured from the normal line, is going to be greater than the angle it has in the slower medium, the refracted angle. And so you see the definite pattern here that as you go from fast to slow, everything that we're measuring here gets smaller, the speed, the wavelength, and the angle as measured from the normal line. Now in our last example, we're starting out with a very similar situation. We're coming in at the angle, but I do want to point out the difference. Before, we're moving from fast to slow. Here we're starting out from a slow medium and moving into a fast medium. So this could be, using what we talked about before, this could say, what if the light's coming from glass or going into the air? Another example would be if you're in the pool and you're actually underneath the water, what happens when you look out? You could say the light rays coming from where they're traveling slower inside the water of the pool, and when they reach the air, what's going to happen to the direction that they travel. So again, a reminder, if there was no difference, if it was staying in the same medium, it would go straight. But now we are speeding up, so things are going to change. We'll go ahead and label the incident angle, the angle it comes in at. But now that it moves to a fast medium, not only will the speed increase, but the angle as measured from the normal line will also increase. So we are going to go ahead and draw that. Instead of straight, we're going to make the angle larger. So I'm going to make it noticeably larger. And we'll label that angle the angle of refraction. And if we were to draw the wave fronts, I'm going to do my best here. You have your wave fronts coming in, but as you go into the faster medium, the waves that pass in here, they start moving faster before the next wave comes in, so that causes them to spread out. And so those waves get further apart. So we can take a look at our wavelength here. This would be our incident wavelength. This would be our refracted wavelength, and you can see that that is larger. Here we've got a normal incident velocity, but here the velocity is greater and in a different direction. So I'm going to draw a larger arrow in that direction. You've got your refracted velocity. So in this case, it's just the polar opposite of what we had before. We were going from fast to slow, but now we're going from slow to fast. And so in that situation, the incident velocity is slower than the refracted velocity, which causes the incident wavelengths to be smaller, closer together than the refracted wavelengths. And then finally, the incident angle will also be smaller than the refracted angle. The third wave behavior we want to discuss today is diffraction. What diffraction is as a wave travels past a barrier, it tends to fill in and bend the areas behind the barrier. So as you see, as we are showing here in these pictures, you have a wave, the wave is coming up in this direction, and as it passes past this black barrier, the part of the wave that should be blocked bends and starts filling in that area. So we have a few different situations we're showing here where it passes by a single barrier. If it passes between a slit between two barriers, you see how it bends in both directions to form more of a circular pattern. Or if it bends around both sides of the barrier, the side behind the barrier that should be blocked, the wave bends in. This is one of the major wave behaviors that people argued about a century or two ago as they were trying to figure out whether light was a particle or a wave. One of the things that they knew that waves did is it diffracted, it bent around barriers. However, light didn't seem to bend around barriers, and that made people think it was more of a particle than a wave. Because a particle, if a particle comes up here, it'll either hit and be totally blocked or it'll pass by, but particles do not tend to bend around like waves do. So what we have here are just a couple examples. We've got the ocean currents coming in, and as they pass by this landmass, you see that the waves that pass by it, they bend around in a circular pattern on this side, and then the waves that come on this side, they bend around in a circular pattern to fill in. They diffract, they bend around the landmass. And then here we got waves coming in through an opening, so it's being blocked by this side and blocked by that side. But as it comes through the opening, you get this circular pattern that is formed as the waves diffract and bend through the opening. If we take a look at the wave simulator again, here we have some waves coming in, and let's go ahead and hit play, and we stop it for a second. And so what you see is the waves come around, they bend, they diffract to fill in that gap. Now if we change the frequency, we're going to lower the frequency, which will make a longer wavelength. So you see how the wavelengths are longer. And what I want you to notice is that as these longer wavelengths come in compared to the first one, they tend to do a better job of filling in that barrier. And this is something that I would like you to know, which is that the larger wavelengths from lower frequency waves tend to diffract more, they tend to bend around the barriers better and fill in that gap. And that goes back to what we had discussed before about the amount of bending being affected by the size of the wavelength. When they were debating about light being a particle or a wave, it turns out that white light has very, very, very small wavelengths, so the diffraction is very difficult to see. So at the time, a few hundred years ago, they were not able to detect the refraction, the diffraction of waves from light like they were from sound or water waves. Once they were able to detect that diffraction, that gave more credence to the thought that light could be considered a wave. And the Fourth wave behavior we are discussing now is absorption. And absorption is pretty simple. It simply means that as a wave passes through a boundary or through a barrier, some of the wave energy will be absorbed, and so the resulting wave is going to have less energy. Here it's shown by a smaller amplitude. So in this example, you've got a wall, you have the sound coming in this direction, and it hits the wall. Now, as we said, with refraction, some of the waves can pass through, but some of them reflect. So you've got the sound coming in, reflecting back. You've got the sound that does travel through the wall here, but there is some absorbed sound. Now, what happens, because sound is a type of energy and you cannot get rid of energy, when you have partial, or when you have absorption, the waves energy can be absorbed and converted into heat. So it's not a very big effect, but those absorbed sound energies do actually get converted into heat energy, and there can be a slight measured increase in the temperature of the object depending on how much wave energy is absorbed. And that is the end of our discussion.